graphing what we call a compound inequality. And a compound inequality is going to consist of basically two inequalities with either the word or and in the middle. And today we're specifically just going to talk about the ones that have the word or in the middle. So this is really kind of like only half of compound inequalities. So to get us started, let's get down some definitions in our toolkit. So again, a compound inequality consists of two or more inequalities, and they're joined by the word and or the word or. So they have the word and or the word or in the middle. Now let's talk about what each of these words mean. What does the word and mean? What does the word or mean? And so, you're familiar obviously with what these words mean, but we're going to talk about what they mean in the mathematical sense. So when we say and, for example, if I say I want a hot dog and a hamburger, it means I want both. I want the hot dog and I want the hamburger. Like if you just bring me the hot dog, I'm not going to be happy. If you just bring me the hamburger, I'm not going to be happy. I want both, right? In other words, in math, it means intersection. So it's what do the two items have in common? If I were to draw a Venn diagram, let's say I have like A and B, it's what do they have in common? Where do they intersect? And that's the key word I think that you need to remember when you're working on solving and graphing compound inequalities. So and means where do they intersect? Where is A and B? A and B is in this middle or intersecting part here that we have shaded blue. On the other hand, the word or, if I were to say, I want a hot dog or a hamburger, think about that. So like if you brought me back a hot dog, I'd be happy, right? So think of like A as being the hot dog. If you brought me back just a hamburger, I'd be happy. Think of B as being the hamburger in this Venn diagram. So if you bring me back just a hot dog, I'm happy. Just a hamburger, I'm happy too. But here's the difference. When we talk about the word or in math, we actually mean one or the other or both. So notice it has this like middle part shaded like we did over here in the and. So when we say or in math, it means you bring me back the hot dog, I'm happy. You bring me back just the hamburger, I'm happy. But if you bring me both, I'm also happy. So one or the other or both. So in other words, in math, we say like union. Or means the union of A and B together. So anything that's in A, anything that's in B, anything that's in both. All right. Let's jump in to going through some example problems. So graphing these is going to be the hard part. Solving them, you're going to solve these compound inequalities just like we've always been solving inequalities. It's the graphing that's the tricky part. So we're going to start off. For example, number 1, we're going to graph this compound inequality. Again, it's a compound inequality because we have two inequalities and they're connected with either the word and or, in this case, or. So we're going to start off by graphing this part here. X is greater than 4. So I start at the 4. 4 gets an open circle, and X is greater than 4 would shade to the right. Now I'm going to go over and graph just this second part here. X is less than or equal to 2. So I find my 2 on the number line. X is less than or equal to, so that gets shaded in because I want to include the 2 as a part of the solution. And where X is less than that would graph down here. So now I graphed each of these parts in isolation. I'm going to combine these two graphs. So combining the graphs would look like this, right? So I'm just literally kind of like recopying them on the same graph. Now, once I combine the graphs, now I need to think about this word that connected these and that made this a compound inequality, the word or. Remember, in math, or means one or the other or both. So we're thinking about like numbers that are solutions. We want our number, we want to pick a number x that could be a solution to this or both. And so think about it. Over here in this section here, all these numbers here are a solution to that part on the left, like x is greater than 4. So if I were to pick the number like 8, for example, is 8 greater than 4 or it less than or equal to 2? Yeah, it is. It doesn't make both of those parts true, but it makes one of them true. So it makes one or the other or both true. So 8 should be a solution. Notice that 8 on my number line is shaded. How about -3? -3. If I were to plug in x equals -3, is -3 greater than 4? No. Or is -3 less than or equal to 2? It is. So it makes one or the other or both of these true. So it's shaded. But let's think about like the number 3. Plug in 3. Is 3 greater than 4? Nope. Or is 3 less than or equal to 2? Nope. So 3 is not shaded. It's not a solution. It shouldn't be shaded. So the union of the two graphs would be this whole thing. This whole thing. This would be my final answer here. All right, let's try another one. So if I have x is less than -1 or x is greater than or equal to 3, again, we're going to start thinking about like each of these separate graphs in isolation. X is less than -1 is going to look like that. So x is greater than or equal to 3 is going to start at 3. It's going to be a closed circle because it's going to include the 3. And x is greater than 3 is going to shade to the right like that. Now we're going to combine the graphs just like we did before. So draw them kind of on the same number line. And remember, we're looking now for the union of the two graphs because this is an or. And again, remember, or means one or the other or both. Where are one or the other or both of these true? Well, basically, when it's an or, anything that's shaded on either part of the graph is going to be a part of the solution. So this is my final answer. That's my graph, my solution. All right, let's try some more practice problems. So those first two, we just had to graph. We didn't have to do any solving because they were already kind of solved for x for us, right? Well, now, what if I have to solve for x in addition? So you're going to solve for x just like you normally would. So 2x is less than -6. If I'm solving for x, I'm going to divide both sides by 2. And I have x is less than -3. And then completely separately, I'm going to solve the other part of this inequality. So -7x less than or equal to -21. I'm going to divide both sides by -7. And when I do, because I'm dividing by a negative number, I have to flip the inequality. So my solution is going to be x is less than -3 or x is greater than or equal to 3. It's really important that in my solution, I have all of this. I've rewritten the word or, and I have both pieces, like both of the inequality pieces. Now let me graph. X is less than -3. So it would start here on the number line. Here's -3. X is less than that. Gets shaded down this way, right? And then we have x is greater than or equal to 3. So here's 3, greater than or equal to 3. We'd shade this in, and we would graph that way. And again, or means where one or the other or both are true. So anything that's shaded is a part of the solution. So there's my final answer. Okay, so number 2, x is less than 2 or x is greater than or equal to 4. Well, here, x is already by itself. X is already by itself. So I don't have to do any solving. I just have to graph. So 2, I start at 2. X is less than 2, shades this way. X is greater than or equal to 4, starts here and shades that way. And again, because I'm looking for where this or this is true, I went where one or the other or both are true. So anything that's shaded is a part of my solution. There we go. All right, let's do a couple more. So again, we're going to solve for x first in both inequalities. So x minus 3 is greater than 8, or x over 2 plus 1 less than or equal to 6. So let's start with the x minus 3 is greater than 8. We're going to add 3 to both sides to get x by itself. So x is greater than 8 plus 3 is 11. And then separately, we're going to solve the other part of the inequality. So x over 2 plus 1 less than or equal to 6. Remember, this x over 2 means really like x divided by 2. So we get rid of our SAD map. We get rid of our subtractions or additions first. So we're going to subtract 1 from both sides. We have x over 2 less than or equal to 5. And then we have to get rid of this x divided by 2 by multiplying both sides by 2. So we're going to multiply by both sides by 2. The 2's cancel. We have x is less than or equal to 10. And I would not flip that inequality because even though I multiplied by a number to solve, I multiplied by a positive number, positive 2. So my solution would be x is greater than 11 or x is less than or equal to 10. So if I were to graph this, I'm going to start with this x is greater than 11. So here's 11. X is greater than 11, goes this way. X is less than or equal to 10, starts here, and shades going down this way. Again, or means where one or the other or both are true. So I would leave all of that shaded. All right, number 4. So again, I'm going to solve for y in each of these inequalities separately. I'm going to use SAD maps, so subtraction or addition first, and then multiplication or division. So 5y minus 3 greater than or equal to 12. So I need to get rid of my subtraction here. I'm going to add 3 to both sides. So I have 5y greater than or equal to 15. And then to get y by itself, divide both sides by 5, y greater than or equal to 3. And then over here, I have 2y minus 3 less than negative 1. So I'm going to add 3. I have 2y is less than 2. And then divide both sides by 2. So y is less than 1. And in my solution, don't forget, I'm going to rewrite the word or because that's a part of my solution. So it's y is greater than or equal to 3 or y is less than 1. So y is greater than or equal to 3 looks like this. And then y is less than 1 looks like that. And again, because this is an or, I want where one or the other or both are shaded. So that whole thing is a part of the solution. Okay. Oh. Sorry, here we go. Okay, so let's do some extension problems. Now that we can solve and graph, we're going to kind of go backwards. We're going to write a compound inequality for each of the solution sets shown below. So number 5, I'm going to write the compound inequality. So I noticed that the shaded region starts here at -2, and it includes that negative 2 was colored in. It was a closed circle. So I know it's going to be either less than or equal to or greater than or equal to. I know I'm going to have that or equal to part. And it's shaded going to the left. So when numbers are shaded going to the left, that means like x is less than or equal to that number. So x is less than or equal to -2. And then over here, this graph starts at 1. And it doesn't include the 1. It doesn't have the 1 shaded. So I'm not going to have the, or equal to that line underneath. But I'm shaded going to the right, or in other words, the numbers that are greater than. So x is greater than 1. And let me just make this, I'm going to rewrite it to make it look a little nicer. But so my answer would be x is less than or equal to -2, or x is greater than 1. So that's the compound inequality that matches the graphed solution set there. And then in number 6, it says all real numbers that are less than -1 or greater than or equal to 4. So all numbers, that's like x, that are less than -1. So it's x is less than -1, or real numbers that are greater than or equal to 4. So greater than or equal to, this part here, is the greater than or equal to 4. So there's my compound inequality that would represent that situation. All right, that's it for compound inequalities with that are like the OR type problems. Thank you so much for watching. Have a great day.